So, hey everyone, hello. Welcome to this meetup. We are we are here for the first time, so pretty excited to meet you all. I was expecting a little more people, but that's fine. We'll do with you guys. But as he said, I'm Ritik. I'm a machine learning engineer at Pine Research. So is he. He likes to call himself deep learning associate. Seriously, there's no difference. But we are both good developer expert in machine learning. And today our topic that we have chosen is decoding end-to-end object detection with transformers. And this is a paper that came out back in 2021. 2020.
Before we can transfer.
Yeah, so it's a pretty famous paper. It's a really complicated paper. But before we go into all of that, I just want to know the show of hands. How many of you are really interested in machine learning? How many of you are, curious about this, about the world of machine learning, about whatever is happening? Really? I think everyone should be curious.
Yeah.
Okay, great. So everyone has some idea about, does anyone know about Pi-image search? What is Pi-image search? Yeah.
It's a module, right?
Yeah.
It's a module.
It's a module. Okay. No, you're talking about a library, but that has been developed by Pi-image search. But she's correct over there. But Pi-image search is a deep learning education company. Okay. We primarily make tutorials on deep learning, computer vision. Our primary focus is computer vision. Having image in the name does that. But so if you scan this, if you take a picture of this, scan it later, or don't scan it, it's on you. No one's arm twisting you. But if you do that,
I am. At least I am.
if you scan this, it will take you to all of the blogs, all of the tutorials that has been published on Pi Research about machine learning. And we go from the very beginning, what is machine learning, all the way till, I think,
Direction
transformers, recent papers that have come out. So if you have, if you are stuck, if you don't know where to go for a particular topic in computer vision, even classical computer vision, not proper machine learning, HOG detectors, canny edge detectors, and all of that stuff, can check our site out. I guess we keep hearing from computer vision and machine learning engineers that all of their careers were kick-started from Pi Research. So that's a lot about Pi Research.
and I leave you to.
Now I'll go through the slides, and I'll go through this. I'll go through this in a very chapter-wise manner. Everyone settled down? Good. So who can tell me what object detection is?
Detecting objects in an image.
No. Great. Anyone else? Anyone wants to build on top of that? Anyone wants to, say why is object detection required? Why is it a problem statement, a task to be solved? Come on now. We are just discussing. And what we would want this talk to be is less of me preaching and more of a discussion between like-minded individuals, where we get to talk, we get to share some nuggets about this paper, and you get to derive from that why would you, be interested in this paper in the first place. So, anyone, randomly, what comes to your mind when you think of object detection?
So I think one of the use cases could be detecting the number plate from a video stream of a speeding car or something on those lines.
Yeah.
So where you can detect the edge points as well as the edges,
Okay.
and hence extract the
Extract the numbers. Brilliant. What's your name?
meager.
Okay. So we got a very nice answer. It was more centered around the application side of object detection. Like, what can object detection do for us? License plate registration or extracting numbers from license plate, or OCRD, which is like a superset of this, optical character recognition, is pretty much one of the derivatives of object detection. But what object detection is, is that I think it is drawing boxes around stuff that we as humans recognize. Okay, and it is tough because when we have a model about this world, when we have a visual language where we understand, okay, this is a desk, this is a laptop, this is a microphone, the pixels that are going into the camera do not have that sense. So that is why that promise statement is tough. And I think we have a video over here where I just move out of the frame, where we show how object detection is possible. So this is exactly what object detection happens. How object detection happens in deep learning. You have a video or you have an image, and bounding boxes are drawn continuously over every frame, and then class probabilities are given. What do I mean by class probabilities? Whether it's a person, it doesn't know it's James Bond. Okay, don't expect it to. Whether it's a person, how much probability that it's a person, it's a gun, or it's one of James Bond's villains. So we go into the classification or the terminologies associated with object detectors. And object detectors, classically, in the old days, and medieval days, like 10, 20 years back, there used to be two types of object detectors. There used to be two types of object detectors. One is a one-stage object detector, and the second is, well, you can read it. And basically what happens is that the images are passed to a block. Think of this block as a black box, as some kind of feature extraction, some kind of signal processing mechanism, which extracts useful features from the images. Like, for example, what would be the key point of classifying a dog? Paws, nose, ears, stuff like that. So it extracts those kind of features from that image and passes it on to another mechanism which classifies whether it's a dog, whether it's a cat, whether it's a horse, okay, whether it classifies based on those features that have been extracted, and then it localizes on the image. With me so far?
Yeah.
Anyone? Okay, so if this is getting too much, if this is something that that is not being easily understandable, just tell me, treat me as your, feedback mechanism. I will tone it down. Equally, if it's like too easy, tell me, I'll step it up a bit. Okay? Good. So that is one-stage object detectors. And usually, convolutional neural networks excel at this stuff. Everyone's heard of convolutional neural networks? They were all the rage back in the old days. Okay. So CNNs are a way of doing image processing and computer vision, and they were particularly good at this stuff. Okay. Now that we could go back to two-stage object detectors, where the same thing happens, but there's an initial set of region proposals. So whatever you're seeing right now, me standing here talking to you about one stage, two stage, boring stuff. So it's your mind is drawing a sort of box and saying, okay, I need to focus on him. I need to focus on the blackboard, right? That's an initial set of guesses that your mind is doing, and you're not really paying attention to the rest of the stuff. That's exactly what is done in the two-stage detector, where you give a set of region proposals in the image, and you say, okay, you have to kind of focus all of the feature extraction on these initial parts and not look at everything else. So that's one stage and two stage object detectors, and that's the end of the story there, because we are not going to be talking about object detectors. There is a problem with one stage and two stage object detectors, and the problem is that we are heavily relied on where the guess needs to be, where the feature is being extracted. Imagine if there's an image of a dog running through a field, and the machine learning algorithm or the algorithm or the black box decides to extract a feature from the grass or the field where the dog is running, it's pretty useless for you. You won't be able to do much with that. So your initial guess or your initial localization of the feature extraction is really important for this methods to be successful. And the solution is that if we go back to here, we can see that this is a makeshift kind of a solution. Does everyone understand this? Like, we have an image, then we put that into a feature extractor, then that feature extractor gives me features, and that goes into a classification and localization, pipeline, and that is giving me the object detection. Like, this is a very makeshift kind of a solution because it relies on multiple components to work in tandem to give you the object detection. And we, as pristine engineers, would want a solution that works end-to-end. We don't come in, we don't say, hey, you need to guess here, you need to fine-tune this, you need to extract features from here. It will do all of it on its own. We just filled in the images of James Bond. So that's a solution that we are in search of. Here it comes the paper, DETR, detecting end-to-end object detection with transformers, detection transformers, DETR. And here I would like to take, I would like to digress a bit, and bless you. I'd like to digress a bit and talk a little bit about why DETR. Okay, because now you know the problem. Anyone here who will repeat the problem for me? Like, what are we talking about? What are we solving here? We'd like to make an end-to-end pipeline. Well, great. Thanks for remembering that. Okay, so we are trying to make an end-to-end pipeline for object detection. And why specifically DETR? Why have we chosen DETR? The reason that we have chosen DETR is that it is an academic paper. And I kind of understand that some of you are just getting into machine learning. Some of you are trying to know more about, what machine learning, what AI is. And all of this is like, yeah, it's good, but it's not for me right now. But I would still like you to, go through this session, take whatever you can, because there doesn't exist, unfortunately, only one unique way where you can go about machine learning. Okay, you almost in all cases will have to find your own way. Everyone in this room who are machine learning engineers will probably tell you a different story as to how they got into machine learning. So the reason we chose this paper is that we talk to a lot of engineers and we talk to a lot of Google developer experts as well about this paper. And one thing that we kind of got back is that this is tough. It's tough to implement, it is tough to read, and it's tough to wade your way through. So we chose the tough part because if we can break this down, make it easy for everyone to understand, like not we as in me and Orito, we as in we, you and me. If we can do that, we can understand this topic, take some nuggets out of it from which we can go back, benefit, and then implement it on our own in 7 days. We are basically good to go. We can tackle any machine learning problem we want. So that is great. So that is the inspiration that we want you to have for going through this session. So DETR, we are kind of zeroed in on DETR right now, detection transformers, end-to-end, and the thing that it solves is an end-to-end pipeline for object detection. Hello everyone. Great. We were just talking about an end-to-end pipeline for object detection, and we'll go through it. So, as I was saying, the problem statement is centered around we have a lot of components that ultimately achieves object detection, but they are kind of clunky. They are put together in a manner that is not elegant, and we want to find a solution to do object detection in an end-to-end fashion. So that's our main goal, and we kind of know the backstory as why we chose this goal. So what does DETR achieve, or what does this elegant new pipeline ultimately achieves in the end? Well, first of all, it views object detection not as a problem where you extract features and then you show those features, or you tell that this object based on a set of features. It says object detection primarily is a set prediction problem. And no need to worry if you don't know what set prediction problem is, or if this kind of feels like too theoretical. We'll go through it step by step as well. Using transformers and parallel decoding. Now, how many of you have heard about transformers? Great. Everyone's heard about transformers. It's all the rage right now. Like CNN was a few years back, right? And so transformers are a particular breed of models that is capable of, directing something called attention, which is a mechanism, which is a way of understanding what needs to be focused on in a particular set of inputs for, a variety of tasks. It can be image classification, object detection, translation, whatever you feed into ChatGPT, those are transformers at the end of the day. Okay. And what it ultimately achieves as a result of using these two is it eliminates duplicate predictions. Now, if you remember the slide that I showed you about James Bond running through, a bazaar and doing James Bondy stuff, you would see that the object detection happening there, the boxes being drawn, is kind of haphazard. It's not very clean. It doesn't track one object. And there are multiple boxes being drawn. Okay, why is that happening? It's because it treats each frame as a new frame, and that it fits into this model. But more than that, it is throwing you duplicates. It is showing you a duplicate box and saying, I don't know, there might be an image here, you tell me, but I think the class probability of an object being here is less than 10%. And we don't want that. We want our models to be as accurate as possible, as well behaved as possible, and we want the predictions to be as close to 90 as possible. Okay, best case scenario. So what DETR achieves as a result of all of this is that it eliminates duplicate predictions. And if you are losing touch kind of right now and thinking that these two things don't make sense, what we are trying to achieve here is tell you that these are the components of DETR, and we will guide you through these components as we go further into the law. So the next question, as we kind of feel like everyone's thinking about this question right now, is what is set prediction, right? And to think about set prediction, let's think about this example. There's an image, and there's two types of classification happening in these images, right? All good? Yeah, please. Yeah. So there's multi-class classification and there's multi-level classification, right? And what is multi-class? Does anyone here have any idea about what is multi-class classification? Any guesses would work as well. Just be,
having more than one classes, like classifying an object, and the possible classes are more than.
Yes. So if you look at this image, there's trees, the dog is in a forest, so the number of classes can be 2, more than 2, whatever. So there's definitely tree, definitely a dog, and it is saying dog 0.9. So it is saying that 90% chance of a dog being present, right? And why is it multi-class? Because there's 2 classes and it's classifying one of them, right? Multi-label, there's multiple labels, okay? So there's a set of labels, there's a set of classes, dog, trees, birds, whatever, and it is predicting which level is which. That is why it's multi-label classification, okay? Everyone's with me till this point? Good? Okay. So multi-label is a set prediction because there's a set of, this is the point where you tell me what I said. Guys, set of labels. Yeah, cool.
So, is the number of outputs in multi-class or is one and this multi-level as multi-class?
Yeah, multi-level will give you the probability of all of the, even if they're like say, for example, there's a bird as a label, and the bird is somewhere in the image, it would say the probability C.
So suppose there was a bird in the in both of the images, and the probability of a bird was 0.6.
Okay.
Okay. So in the multi-class, because the probability of the dog is maximum, only the dog will be random.
Yes, this is a very good question. So what she is asking is, like, so for example, there's a bird in both of these, but like whichever class will have the maximal probability will only that is shown, and the answer is yes, because it is a multi-class classification, right? And the class which has the maximal probability, the object detection model or the classification model will treat that particular class as the primary class present in the image. Okay, it won't go into the further details of whichever other objects are present. Cool. So we are good with that. Multi-label is a way set prediction happens in computer vision. Does that make sense to everyone? Why is it called set prediction?
So can I say that set prediction is nothing but multi-label classification?
Yes. Yes. In the context of multi-level classification, it is nothing but multi-level classification. But there's a looming danger here. And what is that looming danger? We'll go into the looming danger before, but this is basically an answer to your question. What is happening? There's dog, tree, cat, human, and this is all like the image is going through binary classifiers, and it is saying, okay, dog is 0.9, but tree is 0.7, cat is 0.1, human is 0.2. So it is 1 versus rest of the labels. Okay, that this is the concept that 1 versus the rest of the labels is treated. Whichever one is maximum is put out. This is for multi-class. Okay, good. Now, what happens in this case? Does everyone understand the problem that we're looking at? The bird had to go and sit on the head of the dog. Now, both of these is 90% probability. Like our problem statement, but a little bit tweaked. Okay, so both of these has 90% probability. And what happens is that the 1 versus rest approach fails. Okay, you can't just go and say that I'm going to go for dog because I like dogs, birds not so much. That's not going to happen, right? So 1 versus rest approach is failing. Now we need to find a way to tackle this. So direct set prediction, a way to predict sets needs revision. Okay, a way to say that you have an image and let's go back to this image. This is the image, and we are predicting a set of labels from this image. And why does it fail? Again, anyone wants to volunteer except her?
That because so basically it's the classifiers gives us same amount of probability for 2 different objects and choose which one is that.
Yes. If it gives us the same amount of probability for 2 different objects, that's no point. That doesn't help us that much. And the correct way to express this phenomena is that if the region proposals are too near to each other, if the bounding boxes drawn on them kind of overlap in a way that is really annoying, you cannot separate them, but you kind of need to because for object detection to happen. How will you say that this is dog? This has to be either a dog or a bird, right? So the 1 versus rest approach fails, and direct set prediction means revision. And in the context of DETR, what is happening is that DETR, and this is not important right now. Okay, this icon, treat this as an icon only. Okay, DETR or a black box model predicts n number of objects. So at the end of the machine learning pipeline, you will get n number of objects, where n is far greater than the number of labels in the image. So if you kind of imagine this image again, there are a lot of bounding boxes here and there, and there's only a few of them, or not even a few of them, there's only a certain version of those bounding boxes in the image which are correct, which is the ground truth level. I think I had, okay. So DETR or your model, machine learning model, is predicting a lot of bounding boxes. You need to match those bounding boxes with the ground truth levels. You need to say that this is the correct bounding box and this is not, so discard it, right? And therein comes something called bipartite matching, which is, I know it's getting theoretical, bear with me. There's, pot of gold at the end of the network. Bipartite matching is a way to do this matching, to say that, this bounding box is useful. It is more or less closer to the actual bounding box that we need. But this one, which is not a tree, not a leaf, not a pod, it's just a random bounding box on the image that we don't need. So that is not useful. And we can figure this out as human beings, as human beings, when we go through these bounding boxes, we can figure this out. But what we need to do is find an algorithm that can figure this out iteratively and, come down to a set of bounding boxes that are as close to the ground truth levels as possible. That's what we need to do. And therein comes the concept of optimal bipartite matching. So what is optimal bipartite matching? It's a mathematical concept from graph theory, often used in computer science and optimization problems. It's a process of pairing vertices from two sets in such a way that each vertex is paired with at most one vertex from the other set, and the total number of paired vertices is maximized. But this is definitions, and it is important to see the definition, feel overwhelmed, feel that, we are not understanding anything, because when we go through the analogies, when we go through the stories that make sense, we will connect these dots and understand this in a better way. Okay? Nothing wrong in definitions, nothing to be feared at all. Let's take an analogy. Okay? There are workers and there are certain jobs. And what is going to happen is we are going to create this matrix, and we are going to put workers over here in the rows and jobs in the columns. And think of this as a way, you can assign, like someone can assign work or tasks to certain workers. So workers and jobs, and this worker one has a certain X amount that they will bill to do job one. Okay, everyone's getting this this diagram. Is this making sense?
Yeah.
Cool. So worker one needs $30 to do job one, $20 to do job two. Job three must be something really difficult, $60 to do that. Okay, and worker two has a similar tariff rate, and worker three again has a similar tariff rate. As an employer, what should your goal be? Don't say layoff. Don't say that, please. What should your goal be?
Give the job to the workers, which will minimize the total cost.
Yes, great. So give the jobs to those workers, which will minimize your cost, because you need to run a company. You need to put food on the table. So give those jobs to those workers that will cost you the least, right? And that's what we have done in this slide, where we have highlighted those jobs for you, like those jobs that will cost you the least for those workers, those corresponding workers. And pictorially, this is what is happening. Okay, workers are getting matched with jobs. If we play this, all of this is done with Manning. Anyone knows Manning over here? What is Manning? Search up 3 blue 1 brown on YouTube.
This safe is
Yes. Everyone got this? What is happening? Should I play it again? Play it again. Good. And that symbol is not important right now. what is sigma, where is sigma coming from. Got it? So it is, first of all, what we are doing is we are drawing all of the lines here. We are connecting jobs to all of the workers. All permutations and combinations are being tried. And then we are saying that, okay, we don't need to have so many permutations and combinations. We need to have one permutation and combination, one combination of jobs and workers that is optimal for us. That is giving us the least amount of cost. Okay? Now, why is that important? We went into a lot of mathematical jargon. We went into, matching and drawing lines like we used to in childhood. Why is that important for object detection? To apply optimal bipartite matching to object detection, we need two things. The two sets, okay, we need jobs and workers. We need the cost associated for that. So that is the $20, $30 thing that you saw. But object detection won't give you those terms in $20 and $30. We need to find a way to express the cost associated with those sets in a way that is meaningful to the algorithm, right? So what if we do this? We say that the two sets are the ground truth, the actual truth, whether an object is present in an image, whether the dog is present in the image or a bird is present in the image or a cat is present in the image. That is your actual ground truth. And the predicted levels, wherever they are, that's y hat. Okay, and this, like, where I was from, that's not important, right? So you have two things, the two sets, the ground truth and the predictions. And like there's an image, let that sink it. And what is happening here is that this is y. Anyone remembers what y is? Ground truth. Very good. And what is y hat?
Prediction.
So what is happening here?
It then is objects and
1%. This.
the real objects that are there. And
Absolutely. It is a ground truth. It is the bounding boxes around the real objects that are present in this image. And y hat is predictions or bounding boxes drawn around this person who I'm not going to name. Okay. So everyone understands what is happening. These boxes needs to be matched. Okay. The better the matching, the lowest amount of cost associated with that matching, the better our object detection pipeline is. Got it? This, like, if you think about this is an end-to-end pipeline. Okay? You don't need to go into feature extraction, then something else, then something else, then something else. This is your problem statement. You have your original bounding boxes around the objects where it's supposed to be. If you have absolutely bad predictions from a bad model of a bad person, and now what you're going to do is you have to match that. You have to match these bounding boxes in a way that cost will go down. Cool? With me? Time to get overwhelmed again. So this is the cost that we were talking about. Unfortunately, we cannot express the cost of matching this bounding box with this bounding box in terms of $20 or $30. We can't do that in object detection. So this is the equation that they came up with. And how many of you feel overwhelmed looking at this? Come on, I expect more people to feel overwhelmed. I feel overwhelmed looking at this, and I've looked at this 100 times. Don't worry. We'll go through this together and we'll see. Everyone's with me? Everyone kind of done feeling overwhelmed? Or need some time to feel overwhelmed? All right, let's dig in. What is this term over here? Phi. Good. It's called phi. But what does it represent? It represents, if we go back to this image, what is this bounding box say? What is, like, is this an object? First of all, tell me, both things say this is an object.
It's an object for the computer visual algorithm because there is a reflection and it looks like a vertical box. So it probably detected the edges, the faint edges.
Okay. Good, good. But in the context of this image, this is your ground truth.
Yeah, so it's not an object.
So it's not an object because when we are talking about object detection pipeline, when we are talking about algorithms that work like this, work with ground truth levels, and once points to someone who can say that what are algorithms that work with ground truth?
Supervise.
Great. So this is not an object because this is nowhere near what these bounding boxes represent, right? Everyone's with me? Good. So when this comes as a prediction from our model, instead of throwing the model out and cursing our date, what can we do? Like, we have to somehow feed this as a mechanism into the model and say that, this is not really helpful, man. This is nothing. So we need a way to express that. And that is fine. Phi is basically a way of saying that this is not useful. This is a no class or no label. Okay? This is not an object. Phi is a way of saying it. So Ci is our class tokens. Okay? Ci is the variable that is going to denote that we have class tokens. Phi is no class or no objects. Right? And E hat or Ci is the probability of that class token. Okay? We know about probabilities right now. We know that dog 0.9 is probability. So P hat of Ci is dog 0.9. Okay? Good? Got it. What is this now? This is a loss function of the bounding box. Okay? And what is Pi and E hat? Anyone here who has any ideas?
Pi is the bounding box on the ground truth, and B hat is the what is it?
E hat is the
Prediction. And the distance between them.
Great. He gets an extra piece. Okay. Okay. So what is happening is he was as close to correct as possible. Okay. Because Bi and B hat is not bounding boxes. It is the coordinates of the bounding boxes. Yeah, it's the same thing. It's the coordinates of the bounding boxes, and that is being fed into this function, which is the loss, which is the box loss function. Okay. And what is the box loss function? It is a way of saying that how similar is the predicted bounding box and the ground truth bounding box. And the way that is achieved is through another mathematical formula. Too much overwhelming, too much pauses. We don't need to go into that. It's just a way of finding the similarity between the predicted bounding box and the actual bounding box. And now I'm going to tell you what this symbol is. It looks like a 1, not really a 1. What it means is that if Ci is not equal to the class token, then you take minus point. Okay? If Ci is equal to 5, then you take y. No, and then you take this point. Okay? If Ci is equal to the no object token, then you take minus 1, otherwise this. And same for this. Ci equal to class token, then you take 1, otherwise this one. Now, we're going to run through a simulation. What if no object token has been predicted? What will this term look like? So run with me. No object token has been predicted. Your class is a no object token. What will this term amount to? Minus 1. Great. What will this term amount to? What will the loss amount to? 0. Why does it need to be 0? Because it's a wrong prediction. It is no object. The bounding box that has been predicted is wrong. So the loss function is 0. Okay, and if 0 is fed back, that does not say tell anything to the model. Okay, because your model needs to correct it only when this CI equal to 5 happens. CI equal to 5 doesn't happen. Okay? And that's when the class probability is being thrown. Now, why is this -1 and why is this +1? Can anyone answer this?
If you have seen how far is the box, like the probabilities that, and then you move the mouse button.
Do we have extra pizzas anymore? We have extra pizzas anymore. He needs to get on as well. Also, can you, what do you think about this? Why is this -1 and why is this?
Yeah, so what actually happens?
Stand up, man.
Well, with a loss of box, it's an actual loss rate. And with, you make an old man's stutter so much. So what happens here is that N box is actually a loss. Loss function, everybody up. And this is not actually a loss, it's a probability. So if you have a good probability, you have this term going up, right? Probability of 0.9 is a good probability. You don't want your loss to be up. You want your loss to go down in this one. So negate that. You want loss of box to go down as it is. Plus that. Right? Makes sense? -1, +1.
Cool. Thanks also for that. And that's where I take my leave because we have more or less 60 slides and I went through 30 of them.
Yes. Yes.
What? So before I take my leave of you guys and also takes over, I would like to understand from you what you thought of this. Like, what did you take away from this problem? What was your one key takeaway? Let me simplify these things. What did you take away from object detection as an end-to-end problem? How was that achieved? Yeah?
Minimize the cost of pairing.
Minimize the cost of pairing. Not bad. That's a really great answer. Anyone else?
For classification, instead of assigning classes, we change the way you look at the problem when we try to thing. You try to look at it from a different angles, but it's all of the same problem.
Yes. What's your name?
Hansen.
Hansen. He had the most brilliant answer because he didn't say that, we achieved this or we did this. He said that we changed the problem. We changed the way we look at the problem for us to make sense of it in an end-to-end way. What we started off with as like CNNs or object detectors or models that were incapable of solving the problem at one go. So what do? We change the problem like, brilliant mad scientists. We look at it from a different angle, and that way we look at it as an end-to-end pipeline. And what is object detection when looked at as an end-to-end pipeline? A set prediction problem, right? Everyone remembers that? Dr. Tower did a few slides back?
Yeah.
Okay. So set prediction problem is what we need to solve for object detection, for images. And that is the why of what we are doing in DETR. Now the how of it, how that will be achieved, what tools do we bring to wage this war, that also will take up.
So, enough of recap. We did object detection and proceeds to do a recap. So we did object detection. We understood what set prediction problem is. We also understood, how set prediction can be a problem. How do we have to tackle that, bypassing and stuff like that, right? So I saw a lot of people coming in and they might not know what we are talking about. So we are talking about a paper called DETR, that is detection, TR is transformers. So again, going back to what Ritvik covered a few slides back, is that we have to look at this problem of object detection. Object detection is just drawing bounding boxes. I can do that. And how you have to, use a transformer or maybe not, how you can make this problem more approachable from an end-to-end pipeline. So you don't need to have a feature extractor like a one-stage model used to do. You don't have localization problems, classification problems, blah, blah, blah. You have just one model, you input an image, you get the object bounding boxes as a whole. So it's an end-to-end pipeline that you train. With me? So a few slides back, he was talking about, that is, Ritik is talking about workers and jobs, and also talked about how bipartite matching works. So if you have just workers and jobs, you would have a column of all the workers and the tariff rates for them doing the job, right? So W1, W2, W3, J1, J2, J3. And we just cut the workers and jobs analogy and now provide you with a more simplified analogy of what we are actually trying to achieve. Is that down truth labels and predictions, right? And what we do here is the ground truth labels are the actual segmentation maps. And I say this again, it's a segmentation map, not an object detection map, because just of the icons, they look pretty nice. And it was not, like, we found it very difficult to actually draw the bounding boxes and show it to you. So just think of it as the bounding box that would give this white highlight, right? Don't think of it as a segmentation task as of here. Just think of it as a way to visualize the problem better. Make sense with me? So what happens is ground truth labels. So this is a dog, this is a human being, these are birds. And these are predictions. And see how the predictions are not up to the mark. Everything is a little bit off, right? And these numbers are the exact numbers that we use with the analogy of a worker and a job. But now what happens is these numbers are the cost function, the L match that he said, -1, +1, and blah, 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 which was the overwhelming equation. And you fit that function using these two variables. That is the ground truth labels, that is Y, and the prediction, that is Y hat. Remember that? And you get values like these. Now, what do you do with values like these? With the worker and job analogy, what we used to do is we had to find out the minimal cost that a job and a worker pair would match, right? And that is how you simplify the entire system. Exactly same thing. We are just going to put that analogy and map it onto this, where what we are doing is we are going to find the minimal logs of each pair. What would that bring us? That would bring us to maybe this dog, this object segmentation or the object bounding box of this dog being very similar to the actual ground. Does that make sense to you? Right? And if you do this iteratively throughout the entire system, the bird is going to match to the bird, the dog is going to match to the dog, and the human is going to match to the human. And you do it iteratively. What happens? It gets better, and closer to the ground truths. The predictions get better and closer to the ground truths. What happens now? What happens now is that you actually have an end-to-end pipeline using detection transformers and also are able to get better prediction. That is the main thing, right? We don't have to use an end-to-end pipeline. The main focus is about getting objects being predicted properly. Now, an end-to-end pipeline is a cherry on top of the cake, right? With me? So this is the same thing, the optimal matching. We just have replaced the worker and job analogy with the icons. And that's a little video of us fixing our managed skills. So what happens is this L match gets replaced with the actual overwhelming equation, and we just substitute that, right? Enough of that. We have successfully matched the bounding boxes. That is the ground truth and the predictions are all successfully matched. Are we done now? That is the problem. Are we done? We are done, I guess. Actually, what happens with an end-to-end problem is that the system being solved, as in the ground truths being matched to the prediction, is not the only thing that we need. We also need, a loss at the end of the entire model for the weights of the model or maybe the parameters of the model to be tuned, right? So think about it. In an image classification problem, which Shamik and Ayush are going to cover, what we have is an image. We classify that image into the multi-classes that we have. For each error, we will tune our model, say a knob here and there, and we get better predictions one after the other, right? So the more iterations or epochs that we go on, the better our model gets. As simple as that. But now with DETRs, having an end-to-end problem has its own caveats. So it's not only about having a bipartite matching and match this prediction to that ground truth and everything is going to get solved. You actually need to match all the predicted labels with the ground truths and also have a loss at the end of the model, like a classification model, for all the losses to backprop properly. Backpropagation algorithms, stochastic gradient descent, and just throwing out jargons because I'm a machine learning engineer. Not doing that. So what we do is the final boss loss. We have come to maybe the last stage of our entire slides, where we talk about the final loss, which is the Hungarian loss. As luck would have it, it's not from Hungary, but I don't know. So what this basically is very similar to what the bipartite matching actually did to us. C minus, plus, iterator, CI, phi, everything is there. You just have to, think about it thoroughly, wherein we use a log probability, and I'll talk about this a little more. Why we use a log, why we use a probability. Let's talk about this first. This is the same thing, right? Everyone remembers the L box. That is you have two bounding boxes, and you have to see how much it matches. If it overlaps, I have a good L box. If it does not, I have a very horrendous L box, and we need to make it as close as possible so that it matches the ground truth. With me? Now, this prediction is a little confusing now. Why? Because this prediction is actually predicting what is inside that box, right? So if you have a box, and remember that video of James Bond where James Bond is going through a bazaar and does James Bondy things, and you have a bounding box around James Bond, and at the top, and the video was a little blurry, at the top it said parcel with a prediction probability of 90 or maybe 80, right? A cat comes in, there is a bounding box around the cat saying cat 80% or 70% or whatever. So see how things are changing now. You have a box as well as a classification on that, like a tag on that bounding box itself, right? So this probability is actually the class's probability, right? And now what happens here is that if you have a bunch of things you have to predict, right? So it's one image, you have a bunch of things to predict. You have a bird, you have a dog, you have a human being, you have a tree, and blah, 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 blah. You have probabilities around each of the objects. Does that make sense? Around each of the objects. And how do you have a global loss? By multiplying probabilities from our high school math. You just multiply probabilities and you get the probability of the entire global loss or global probability, let's say. Let's take that for matter, right? Probability goes from 0 to 1. And when you multiply anything of that range, what do you get? Anything of that range. 0.5 to 0.1, right? Do we really like that? It gets smaller, like the probabilities get so tiny that the global loss is kind of way off the chart. You don't even know that whether it's a proper prediction or not, right? What people have done is they have introduced this log term inside of this probability, so log of this probability, and just for the sake of, again a jargon, because I'm a machine learning engineer, this is likelihood. So probability, this part is likelihood. Can I draw on the?
Yeah, yes. Yeah, you can click on that.
Not working. This is like no worries. So this is likelihood, and log likelihood is something which talks about the log of the likelihood. And why do we like log so much? So in a very hand-wavy gesture, this is your Cartesian coordinates, first, second, third, fourth, right? And the log goes from the fourth quadrant to the first quadrant. Negative infinity to 0, right? Negative infinity, remember. It's not, there is no, it's a bottomless pit. So negative infinity to 0, it's a monotonous function. And when you have this log term inside of this probability, now things get interesting. It's because it's a monotonous function, it's differentiable. We like differentiable because the models can be trained with calculus differentiation, right? Don't have to go into that. It's a monotonous function, we like it, right? Now, the monotonous function also gets mapped from negative infinity to 0. Losses get mapped from positive infinity to 0. It has, like, we have actually turned this entire probability thing into a loss function, but not yet. What is this one thing that we need to have this range go from not negative infinity, but positive infinity? Inverse it. Minus 1. Negative, right? We just inverted that, so it goes from the first quadrant to the fourth quadrant for that matter, positive infinity to 0, right? This is a good loss function. Loss function, add it up. And why do we need this to go from I to N? Let's just not talk about the range. I to N doesn't matter. Why do we need a summation here? Anybody? Remember how I said that probabilities need to be multiplied? But log of probabilities need to be added. Right? Not so overwhelming, is it? So this is another of the random things that we do. So this is Hungarian loss, and we take it up. We talk about only this box, which comes from our previous equations. That is this, right? So that kind of brings me to an end to this entire session. As in, I hope you all will go back home, think about object detection as an insect person would do, and go to archive and maybe download the paper called DETR and just read through it. We are recording this, so it will be up within a day or two. You will have these slides, so go back home, take a look at the slides, and also think about how DETR would work. Now, everything after this, because there are a bunch of slides that I'm going to pretty quickly skim through, is kind of like a bonus which is being added to it, right? So what we did is object detection. We also understood DETRs. We also understood bipartite matching. We also understood Hungarian matching. Stop, what it throws, stop. How many things? So that is why, just to top up, to get you all marinated for what could be done. As in, how do you approach a problem and also the architecture of the entire model. So I think everyone is familiar with the term architecture of a model, right? So a model is a neural network. Neural network has weights and biases. If you have a bunch of weights and biases, and weights and biases is also a company. So if you have a bunch of weights and biases, you form a layer of neurons. If you have a bunch and stack each layers up, you have a deep learning model. Everyone is familiar with that. So I'm going to go a little bit further and may take you all through the DETR architecture. And also, if you have any pointers for me, as in some questions, I would try to answer if I have the answers to them. So the question is, do you really need attention again? Why do we need attention? What is attention? Attention is just, hey, pay some attention. That's all. I'll ask you something. I'll have an image. You have to pay attention to that image. That is what we humans do, right? So with a convolutional neural network, that is CNNs, and we have a bunch of visualization techniques, we found out that the models can visually localize or attend to parts, right? But there was this paper called Attention is Only Need, which is a seminal paper published in 2017. It talked about how we can actually perform attention and not have attention as a cause for like an effect of a model. We can actually perform this localization and talk about it. So that's another paper, and that paper introduced transformers. So what we are going to use is detection transformers. So a little bit about transformers. So that is where attention comes in. So by pattern matching, we did this. Transformers has an encoder and a decoder. So a little icon, that's all. No need to get into what transformers are, how do they work. Just an icon, this is transformers, it talks about attention. And attention mechanism segregates information of the entire input sequences. These are also certain jargons that I'm going to throw it out in the open for people to get a little curious about what transformers are, how do they work before getting into DETRs. And if you know transformers, very good. And if you don't know transformers, and this is a segue into my company, if you don't know transformers, this is a link of a YouTube live that we did, that is me and Ritvik did, on transformers and solely transformers. So if you want to nap a screenshot of this or maybe a picture of this, feel free to. This is just us blabbering about transformers for maybe, I don't know, for maybe 1 to 2 hours. And we did get a lot of engagement and people found it really, a thing that to start transformers with. So if you want to start transformers and looking for a guide, here you go. And this is the overwhelming slide, another overwhelming slide where let it sink in, goes through the entire architecture, and I'm going to talk about the entire architecture in a very step-by-step manner. So CNN backbone, what does this do? So this is the input image, right? Everybody knows this is the input image. Goes into a CNN backbone extracts a feature. Now, how ironical would it be if I told you that this is a first stage transformer detection algorithm, just like what we dissed about. In the olden days, we had this feature extractor module, we had localization and all that stuff. This is the same thing, right? But the only problem is with the feature extraction module in the olden days, that could not be trained, or that was trained in self or handcrafting. People were sitting there and kind of providing a non-machine learning algorithm to do some feature extraction, and that feature used to be downstreamed into the second stage and whatnot. But the entire architecture here is an end-to-end architecture for one simple reason, is that if you get prediction and if you get loss, the loss is going to backpropagate through the entire thing. Not leaving onto this, not leaving onto this, not leaving onto that, the entire thing. So it's an end-to-end solution, right? And CNN's activation maps, this is the encoder. Encoder does a bunch of things. The decoder does a bunch of things. And as you think about encoder and decoder, so this encodes a lot of things. This just takes the encoding part and decodes it into a prediction that we have, right? Simple enough. And these are some jargons that I'm not going to work on. This is the CNN backbone. So CNN's activation maps, that's it. Bunch of jargons again, bunch of jargons. This is the encoder, just the encoder part where the CNN backbone on the activation maps come in, flowing to the self-attention of blah, 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 or the layers, and they go out to the decoder. The decoder, the encoder thing comes in, the encoder representation comes in. We have the decoder decoding the bounding boxes, right? And the bounding boxes get into small layers called FFNs. FFNs stand for Feed Forward Network, FFN. And Feed Forward Network gives you the predictions, right? And that is the entire thing coming up again. And looking back, what we did was not about, talking about DETRs. We did not do that. What we did was try to indulge in a class of people who are pursuing machine learning or wanting to understand machine learning, to talk about a paper which was not that talked about, and also understand how we can visualize or perceive a problem in a little twisted way, right? I say twisted because it's not the normal way of doing a slide or a talk on DETRs. DETRs is architecture, train them, look at code, done. What we did is, what is object detection, right? We went to the old days, we set the problems. The problems were initial guesses and lack of global context. So, good problems. Solution? Solution was to end-to-end model. End-to-end model is set prediction. What we need is set prediction. Set prediction is, what is set prediction in bipartite matching? We did that. We also went forward talking about transformers, not that much. transformers and parallel decoding, wherein transformer can give you the predictions in parallel. So parallel and decoder, so decoding, parallel decoding. And we talked about the architecture, and the collab notebook is linked to my slide, right? This is the collab notebook that talks about DETRs and just the inference part of DETR. So a DETR actually exists and the models can be used. You can use it on that latent syncing image that we did in this collab notebook. I'm not going to run that too much for one day. And this should also give you a segue of how to decode any paper, not just DETR. So if you want to decode any paper, read the paper, think about how you are going to teach somebody, not the way, you are going to research into that area rather teach that area. So what we did is, me and Ritvik, we sat down, we thought of taking DETRs up. We read the papers. We also went into the collab notebook, did a bunch of coding. We got the inference results. Things were beautiful. But the problem what we faced is, how do we come up with some slides wherein the idea of decoding any paper comes into play? So think about a problem. What does that problem solve? How does that problem solve? Does it even solve the problem? These are the questions that should always come up to your mind. And also a little segue into what we are trying to do as in me and Ritvik. From tomorrow, that is, tomorrow is a Monday, right? So we at PyMed Search always come up with an open source blog post at every Monday. We also have a newsletter coming up. So what we did is we took this to another level. We pitched this idea to our managers and they really liked it. So what we are going to do is we are going to cover this decoding any paper style of blog post, which is open for anybody. So come on in, grab your first, kind of blog post. If you have any queries, you can directly tweet to us. And that's a little spoiler that we gave. Right? So, interested people? Little bit? Okay. Nice. And a lot of thanks. I would like Ritvik to be on stage for a lot of thanks. See how it feels when you're just sitting there and... So if you do Meta AI, if Shmidu were, if you are watching this on Twitter, we did cite Meta AI for this lovely paper, and TFUC Mumbai for inviting us, for having us speak about this very less spoken of a paper. And these guys.
To this lovely institute, university, to every one of you who came here on a Sunday afternoon, missing your lunch at home, and listening to us talk about ordering boxes, thank you. What would really make our day is not, tag us on social media, not tweet about this paper, not, tag us on pictures that you have taken. Read the paper. Read any paper that you found overwhelming, that you could not decode a while back, a month back, 2 years back. Apply that flowchart that he showed of how you can identify the problem that needs to be solved. What are the steps they are taking to solve it? Does that even solve it? And then the proposed solution. And see if you can crack it. And what I want each one of you to do today is go back home, read any paper, read the toughest paper you had in your life at this point, and try to see if you can decode it, make sense of it, and understand it a little better using that flowchart. And if you can do that, what's stopping you to learn the whole of machine learning, right? Because I can promise you, you will be able to do that. So that's all. And yeah, last but not the least, our company for allowing us to do this. That's all we had to say. Blabber Award. Thank you guys.